All right, this video is on applications of equilibrium constants. It's a lecture note paper that looks like this. And we'll only be doing part of this packet. It'd be too long of a video. So I'll be splitting this into parts. And so this will basically cover the first page and maybe that last problem or the first problem on the second page. Okay, so at this point, so far we have talked about the value of K, okay, Kc or Kp, doesn't matter which one, and that the magnitude of K indicates the extent to which a reaction will proceed. So this is your first bullet point at the top. And so what we just learned, previously is that we have two situations where K is greater than 1 or K is less than 1. We know that if K is greater than 1, it's a product-favored reaction. It means that products are produced in great amounts. And if K is less than 1, then it's referred to as a reactant-favored reaction. Not a lot of product. Okay. However, K allows us to do a couple other things, and these are your 2 bullet points that you'll fill in. The first one is that it allows us to predict the direction in which a reaction will proceed to reach equilibrium. And this is a huge point, and this is the topic of this video. The second thing that K allows us to do is to calculate the concentration of either the reactants or the products when equilibrium is established. Okay, and that's kind of the second idea in this section that will be the second video. So 2 big ideas that K allows us to look at. All right, so I'm going to get rid of this, and we're going to jump around because the way I have this set up is probably not the smartest. So I know there's a problem and all that good stuff, but I want you to jump down where there's your bullet point and it says reaction quotient Q. Okay? So now notice this is capital Q. This is not lowercase q as in heat, okay, or heat, I guess. This is capital Q, okay, which is called the reaction quotient. Now, what Q is it's a number or a value that's obtained by substituting either concentrations or partial pressures into a K expression to determine the equilibrium status of a reaction. Now, that seems like a lot of information in one sentence, okay, and I'm going to show you how this is used. I refer to Q as the fake K. Now, that's not like a real like nickname, or you'll never see that in a textbook. That's just me talking. And so I often refer to Q as being a fake K, and you'll see why in just a minute. So if we go back up to where we have this reaction, okay, so it says consider this reaction, and of course it's the famous Haber process that is always used in equilibrium discussions, and it's an all gas reaction. So they give you this reaction and they say, suppose we place a mixture of 2 moles of H2, 1 mole of N2, and 2 moles of NH3 in a 1 liter container. How will this mixture react to reach equilibrium? Will the N2 and H2 form the ammonia, or will the ammonia break down? Okay, so you might be like, what? How am I supposed to answer this question? Well, we're going to answer it by calculating something called Q. Okay? And Q is basically the exact same as how you write a K value. So I'm going to do a Q here for this reaction, and it's products over reactants. So concentration of NH3 squared over concentration of N2 times concentration of H2 cubed. But we use Q when we are unsure of the equilibrium status of the mixture. So see, in this situation, I have a container. I have some N2, some H2, and some NH3 in this container. They tell me all 3 are present. Okay, so the first question that I think we want to discuss is it possible that this container with all 3 species is at equilibrium? That's the first big question. And of course the answer is it's possible. Sure, it's possible. I have all 3 components of the reaction in the container. So it's absolutely possible that it's at equilibrium. But I don't know if it's at equilibrium. And I'll only know if it's at equilibrium if I have a Kc value. See, they told this to me and I forgot to write it down. Of 0.105. They tell me that Kc is 0.105 for this reaction. So what I'm going to do is use this idea of this fake K, which we call Q. Because, see, we're unsure if this reaction is at equilibrium. It might be, but it might not be. I don't know. So I'm going to calculate a Q, and we're going to see what happens. Now, they gave me moles, but they also told me that they told me that the volume was 1 liter. So, in fact, the moles are actually my molarity. So, the molarity of my NH3 is 2. Let's see, the molarity of my N2 is 1. And the molarity of my H2 is 2, right? Did I do that? Yeah. And it's cubed. Okay, so let's see. 2 squared is 4. 2 cubed is 8. 8 times 1 is just 8. So my Q value here is 0.5. Now, one thing should definitely stick out, and that is my Q value does not equal my Kc value. And so what we can conclude from this is reaction is not at equilibrium. Because see, if it was at equilibrium, Q would equal K. All right, and that's the big takeaway here. So in this case, my Q value is larger than my Kc. Okay? So, see, my Q value is larger than my Kc. So for this reaction to reach equilibrium, my Q must decrease. Okay? Right? 0.5 has to go down to 0.105. So in order for Q to decrease, now remember, Q is a ratio of P over R. Okay? So I have two situations here. I can either decrease my reactants and increase my products, or I can do the reverse. I can decrease my products and increase my reactants. See, I can either send my reaction in the forward direction or in the reverse direction. The kicker is which situation will allow me to decrease the value of Q. Right? Well, the value of Q here is only going to decrease if this ratio gets smaller. And for that ratio to get smaller, my products would need to get smaller and my reactants would need to get bigger. See, it only works that way. If you flipped it the other way, Q would get bigger. So, how are my products going to get smaller and my reactants are going to get bigger is only if my reaction is if my reaction is proceeding from right to left. So the question here was, what happens? Does this and this react to form this, or does this break down to form this and this? We just said this needs to decrease. So the NH3 is going to decompose and make more of these two. So we will say NH3 decomposes to make the N2 and the H2. And what is sometimes said is that the reaction proceeds or moves from right to left. Okay? So we were able to do a couple things in this situation. We were first able to to decide if this reaction was at equilibrium, and once we decided that it wasn't, we had to decide which way it was going to move to get to equilibrium. Okay? So now, as you may have guessed, there are three possible situations, and we kind of already talked about this. And that is that Q can equal K, and this is underneath, you see those bullet points. Q can be greater than K, which is what we just saw, or Q can be less than K. So if Q is equal to K, reaction is at equilibrium. Life is good. Okay. If Q is greater than K, this was the example we just had, remember the 0.5 and the 0.1. So if Q is greater than K, the reaction will move right to left to make more reactants. Okay, it will lower Q's value until it reaches the value of K. Of course, the opposite's going to be true if Q is less than K. Then the reaction will move left to right to make more product and to increase Q's value. So you remember Q is P over R. So if the reaction's making more product, this is getting bigger and this is getting smaller, then Q, that's a Q. Q is going to get bigger, which means the Q would get bigger enough to equal the K. All right, so it's all a discussion of how does Q eventually become the value of K. This is not worth memorizing, this whole thing. This is just worth critically thinking about. So now there's two problems, and that will conclude this video, but it's all about predicting which way the reaction's going to go. So we'll do them together. So the first one gives me a reaction of H2 plus I2 yields 2HI. It's all gas. And they give me a KC, and it's 50.5. Okay, so it says predicting which way the reaction will proceed to reach equilibrium if we start with this much HI, H2, and I2 in a 2-liter container. 2 liters, be careful, right? You'll have to do a molarity. So again, I'm going to calculate a Q because I'm unsure of what the condition of this reaction is. Is it possible it's at equilibrium? It's possible all 3 things are present, so we have to find out. So remember my Q is the same thing as my K expression. Now I need to calculate some molarity, so I'll jump down here. So HI is going to be, let's see, what was it? 2 times 10 to the negative 2 moles over 2 liters. So that's going to give me 1 times 10 to the negative 2 molarity. Concentration of H2, let's see, was 1 times 10 to the negative 2 divided by 2 liters, which is going to give me technically, let's see, 0.5 times 10 to the negative 2, which isn't really written correctly, but, you know, that's a, oops, nope, that's this, right? Oh, no, sorry, that's this. Or 5 times 10 to the negative 3, right? 1, 2, 3. And then the concentration of I2 is 3 times 10 to the negative 2 divided by 2, which is going to be 1.5 times 10 to the negative 2. Now that I have my 3 molarities, I can plug them in. Right, being careful that I don't forget to square my concentration of HI, I can come up with my Q value. Let's see, I got a Q value of 1.33. Right, so in this case, Q is much less, I'm going the wrong way. Q is much less than K, right? K is 50. So I need to increase Q, which means I need to make more product. Remember, P over R, P has to get bigger, so this reaction is going to run left to right. Okay, so the H2 and the I2 are going to make more HI is kind of the answer to that reaction. And then the last one is a KP question. I think it's on the next page. And it's the reaction to SO3 in equilibrium with 2 SO2 and O2. Let's see, they give me a KP. It's 0.338. They say calculate the value for Q, okay, and notice they call it QP because it's partial pressure. So partial pressure of SO2 squared, partial pressure of O2, remember I'm not using my brackets, partial pressure of SO3 squared. And they just flat out gave me my partial pressure, so I'm going to plug them in. So let's see, SO2 is 0.41. I'm going to square it. O2 is 2.5. And SO3 is 0.16, and I'm going to square it. When all is said and done and I calculate my Q, I get 16.4. So in this case, it's the opposite of what we just saw, in that Q is greater than K. So I have too much Q. Remember, it's P over R. All right, so that's the key to all of this. If Q is too big, I need to make my product smaller, which means my reaction will go right to left, and my O2 or my O2 and my SO2 are going to react to create more SO3. So in this case, the reaction's going this direction to establish equilibrium. Okay, so that is the discussion on how we can use this value of Q, that's called reactant quotient, to first determine if a reaction is at equilibrium, and second, to determine in which way a reaction will proceed. Will the reactants make products, or will the products make reactants to establish that equilibrium?